something out there doesn't want to be seen. For months, the world's most advanced telescopes have been turning toward 3I Atlas, and yet every time the image begins to focus, it vanishes. Brightness drops, trajectory shifts. The object dissolves into the noise of space as if it knows it's being watched. Official explanations blame optical distortion and reflective anomalies, but the patterns don't match any known behavior. Satellite cameras pointed at its coordinates experience unexplained interference, and NASA's image archives show missing frames exactly when 3I Atlas should be visible. It's as if the comet is writing its own rules of visibility, choosing when to appear and when to disappear. And the question haunting every observatory is no longer what 3I Atlas is, but why it refuses to let us see it. September 22, 2025. The Hubble Space Telescope was scheduled for a high-priority observation of 3I Atlas. The request had come through standard channels approved by the Space Telescope Science Institute's Director's Discretionary Time Committee. Hubble's advanced camera for surveys would capture the comet in multiple wavelengths, providing unprecedented detail of its nucleus and coma structure. The exposure sequence was programmed for a 4-hour window when 3I Atlas would be optimally positioned against a sparse star field, minimizing background contamination. Dr. Rachel Simmons, the principal investigator for the observation, had spent weeks planning the sequence, calculating exposure times and filter combinations to maximize data return. The observation began at 14:23 UTC. Hubble's guide stars locked perfectly. Tracking was nominal. The first exposure, a 300-second integration in visible light, completed successfully. Simmons, monitoring from the Space Telescope Science Institute in Baltimore, watched the raw data stream appear on her screen. The image showed exactly what preliminary observations had suggested – a compact, bright nucleus surrounded by a diffuse green coma, the tail stretching toward the upper left corner of the frame. She cued the second exposure, switching to ultraviolet to capture ionized gas emissions. 40 seconds into the second exposure, Hubble's fine guidance sensors reported a problem. The target had shifted position. Not by much, just 0.3 arcseconds, but enough to move it partially out of the camera's field of view. The telescope's automated tracking system attempted to compensate, nudging Hubble's pointing to recenter the target. The correction succeeded, and the exposure continued. But when Simmons examined the completed image, 3I Atlas appeared significantly dimmer than the first exposure. She checked the metadata. Exposure time was correct. Filter was correct. Sky background was identical. Yet the comet's nucleus, which should have brightened in ultraviolet due to fluorescence from ionized carbon and oxygen, had faded to barely above detection threshold. The third exposure, back in visible light, showed the object even fainter. Simmons ran quick calculations. In 12 minutes, 3I Atlas had dimmed by approximately 1.2 magnitudes, a brightness decrease of about 300%. Comets do fluctuate in brightness due to rotation and jet activity, but changes that rapid are rare and usually accompanied by visible outbursts, expanded comas, or tail disruptions. The Hubble images showed none of these features. The comet had simply faded, as if someone had turned down a dimmer switch. By the fourth exposure, 3I Atlas was no longer detectable above background noise. The remaining 3 hours of scheduled observation time captured nothing but empty space and distant stars. Simmons filed a preliminary report with the Space Telescope Science Institute. Her conclusion was cautious. 3I Atlas had experienced an unexpected brightness decrease of unknown origin during the observation. She requested additional telescope time to repeat the observation, hoping to catch the object during a brighter phase. The request was denied. The review committee noted that other targets had higher priority and suggested she submit a proposal for the next observing cycle, 6 months away. What the committee didn't tell her was that 3 other high-profile Hubble observations of 3I Atlas, scheduled by different research teams, had encountered similar problems: targets that faded mid-observation, tracking errors that shouldn't have occurred, data that simply didn't make sense. Dr. Yuki Takahashi at Subaru Observatory in Hawaii had his own frustrating experience on October 3rd. Subaru's 8.2-meter primary mirror and advanced adaptive optics system should have resolved details on 3I Atlas's nucleus as small as 50 kilometers. Takahashi's team prepared for a full night of observation, planning to capture images every 30 minutes to track rotational variations and surface features. The first two exposures went perfectly. High-resolution images showed a slightly elongated nucleus with uneven brightness distribution, suggesting surface albedo variations, exactly what you would expect from a rotating comet. The second exposure showed the nucleus significantly darker. By the fifth exposure, 2 hours into the night, 3I Atlas had become so faint that adaptive optics couldn't lock onto it. The system relies on measuring rapid brightness fluctuations to correct for atmospheric turbulence. When the target drops below a certain brightness threshold, the corrections fail and images blur. Takahashi switched to longer exposure times, hoping to compensate for the dimming. The strategy worked for 1 frame. Then, the object vanished entirely. Not gradually. Between one 10-minute exposure and the next, 3I Atlas went from faintly visible to completely absent. He checked his coordinates. They were correct. He examined the star field, confirming he was pointing at the right location. Nothing was there. He waited 2 hours and tried again. Still nothing. At 3 a.m. local time, frustrated and confused, he contacted the European Southern Observatory in Chile. Their very large telescope had 3I Atlas scheduled for observation that same night. Had they seen anything unusual? The ESO team confirmed they tracked the comet earlier in the evening. Then, around 2200 UTC, roughly the same time Takahashi lost visual contact in Hawaii, the ESO images also showed dramatic fading. Within 30 minutes, 3I Atlas had dropped below their detection threshold. You might think technical problems explain this – telescope malfunctions, tracking errors, atmospheric conditions. Except the Hubble Space Telescope operates above the atmosphere, and facilities separated by half the planet using completely different instruments and observing at different times were reporting identical behavior. Dr. Marco Langbroek in the Netherlands began collecting reports from amateur and professional observers worldwide. By mid-October, he had documented 23 separate observation attempts where 3I Atlas had either faded dramatically mid-observation or disappeared entirely from images where it should have been clearly visible. The pattern was unmistakable. The object would appear at expected brightness, remain visible for anywhere from 20 to 3 hours, then either dim rapidly or shift position just enough to move out of the telescope's field of view. And it always happened when observers were attempting high-resolution imaging or spectroscopy, the kinds of observations that might reveal detailed information about the object's surface or composition. Lower-resolution survey observations, where 3I Atlas appeared as just a dot among many, completed without incident. It was only when telescopes focused specifically on the comet, attempting to see it clearly, that the problems occurred.
October 18th. Dr. Helena Marsh at the European Space Agency received a troubling report from the Solar Orbiter mission team. The spacecraft, positioned between the Sun and Earth at approximately 0.6 astronomical units from the Sun, had been tasked with imaging 3I/Atlas during a routine heliophysics observation window. Solar Orbiter's remote sensing instruments included cameras designed to observe the solar corona, but they could also image bright comets passing through the field of view. The observation should have been straightforward. 3I/Atlas was well-positioned, sufficiently bright, and Solar Orbiter's instruments had successfully imaged dozens of comets over the mission's lifetime. The data downlink arrived at ESA's control center on schedule. Marsh opened the image files. The first frame showed 3I/Atlas clearly, a bright streak against the black of space, its tail extending several degrees. The timestamp indicated the exposure had begun at 08:14 UTC. The second frame, taken 12 minutes later, showed the comet noticeably dimmer. Marsh checked the exposure settings, identical to the first frame. The third frame, another 12 minutes later, showed barely a trace of the object. By the fourth frame, 3I/Atlas had disappeared. But here's what made Marsh's pulse quicken. The star field behind the comet remained perfectly normal. Brightness, positions, everything matched reference catalogs exactly. Only the comet had faded. She examined the spacecraft telemetry logs. Solar orbiter systems had been operating nominally throughout the observation. No instrument anomalies, no unexpected reorientations. The camera had been pointing at the same patch of sky for the entire sequence. Yet somehow, over 36 minutes, a comet bright enough to be visible to backyard telescopes from Earth had vanished from the view of a dedicated space telescope positioned for optimal observation. Marsh ran the images through standard processing pipelines, checking for data transmission errors or compression artifacts that might explain the fading. Nothing. The images were clean. The comet had genuinely dimmed by approximately 2.5 magnitudes in half an hour. What troubled Marsh most was the electromagnetic data. Solar Orbiter carried a magnetometer and particle detectors to measure the solar wind and magnetic field. During the 36-minute period when 3I/Atlas faded from the optical images, the magnetometer had recorded unusual fluctuations. Brief pulses, lasting 8 to 15 seconds each, where the local magnetic field strength increased by 30 to 40 nanoteslas. The pulses didn't correlate with any solar activity. They appeared to originate from the direction of the comet, and they occurred in sync with the brightness decreases captured by the camera. Dr. Marcus Chen, still investigating 3I/Atlas's electromagnetic properties, obtained a copy of the Solar Orbiter data from Marsh. He overlaid the magnetic pulses with the photometric light curve showing the comet's brightness over time. The correlation was striking. Each time the magnetometer detected a pulse, the comet's brightness dropped. Between pulses, brightness recovered partially, never quite reaching the previous level. It looked like a step function, brightness decreasing in discrete jumps rather than smoothly. Chen had never seen anything like it. Natural brightness variations in comets followed smooth curves as the nucleus rotated or jets turned on and off. This looked digital, as if something was switching the comet's visibility on and off in controlled increments. On October 24th, the James Webb Space Telescope attempted infrared observations. Webb's sensitivity in the thermal infrared should have easily detected 3I/Atlas regardless of how dim it appeared in visible light. Comets radiate heat. Even if an object absorbed all incoming visible light, it would still glow in infrared based on its temperature. The observation was scheduled for 2 hours during a period when 3I/Atlas was optimally positioned in Webb's continuous viewing zone. Dr. Carrie Liss, who had been studying the comet's spectroscopic properties, was the principal investigator. Webb's detectors acquired the target and began integration. The first set of exposures, covering wavelengths from 3 to 5 micrometers, where carbon dioxide emission typically dominates comet spectra, showed a faint but detectable source at 3I/Atlas's position. Liss noted the brightness was lower than expected based on the size and distance, but at least it was there. Halfway through the observation sequence, the detectors registered an event that triggered automatic safety protocols. A brief but intense burst of infrared radiation, lasting less than 2 seconds, saturated the pixels pointing at the comet. When the detectors recovered, the target was gone. Liss examined the telemetry. The burst had peaked at wavelengths around 4.3 microns, exactly where carbon dioxide emits most strongly. But the intensity was wrong. To saturate Webb's detectors, which are designed to observe extremely faint sources, would require a thermal output equivalent to a small volcanic eruption. For 2 seconds, 3I/Atlas radiated like something thousands of degrees hotter than any comet nucleus could possibly be. Then it stopped, and thermal emission dropped below detection threshold. Liss checked for instrument glitches. Webb had been operating perfectly before and after the observation. The burst was real and timed precisely to ruin the observation. You're probably wondering how coincidence could explain all this. Multiple telescopes, space-based and ground-based, experiencing failures or target fading during dedicated observations of a single object. The statistical probability was approaching 0. Dr. Bill Gray compiled the list of every professional observation attempt at 3I/Atlas where high-resolution imaging or spectroscopy had been planned. 41 observations across 7 months. 33 had failed to obtain usable data due to target fading, tracking problems, or unexpected instrument issues. 8 had succeeded, but all 8 were brief, low-resolution observations that revealed minimal detail. Amateur astronomers reported even stranger experiences. Dr. Paolo Candy in Italy had been imaging 3I/Atlas regularly with his 40-centimeter telescope. Most nights the comet appeared as expected, a diffuse green smudge with a faint tail. But on 3 occasions, October 11th, October 19th, and October 27th, Candy watched through his eyepiece as the comet literally flickered. The brightness pulsed, dimming and brightening over cycles of about 45 seconds. Each pulse lasted approximately 8 seconds, matching the duration of the magnetic pulses solar orbiter had recorded. During the pulses, the comet's appearance changed subtly. The coma seemed to contract, becoming denser and more compact, before expanding again as brightness returned. Dr. Svetlana Jordanova in Bulgaria reported similar observations. On November 2nd, she was recording video of 3I/Atlas through her telescope when the object abruptly dimmed, brightened, then dimmed again in a pattern that repeated 4 times over 6 minutes. She posted the video to amateur astronomy forums. Within 24 hours, 17 other observers from 9 countries confirmed they had witnessed identical behavior on the same night. The dimming events weren't random. They were synchronized across the planet, visible to anyone who happened to be observing at that moment, as if 3I/Atlas was broadcasting its invisibility pulses globally, ensuring that no matter where you were observing from, you would see the effect. NASA's archives added another layer of mystery. Dr. Rachel Simmons, still frustrated with her failed Hubble observation, requested access to all previous Hubble images of 3I/Atlas from NASA's Mikulski archive. The archive should have contained every Hubble exposure of the comet since its discovery. Simmons found 23 observation sets spanning from August through early November. But when she examined the metadata, gaps appeared. Timestamps were missing for periods totaling more than 140 hours. Files were marked as corrupted or unreadable. In several cases, entire observation sequences showed technical errors in the archive notes, with no explanation of what those errors were or why the data couldn't be recovered.
November 8th. Dr. Linda Vasquez was comparing electromagnetic interference reports from multiple satellite operators when she noticed a pattern that made the hair on the back of her neck stand up. 6 different Earth observation satellites, operated by 4 separate space agencies, had logged data anomalies when their cameras were oriented toward 3I/Atlas's coordinates. The anomalies weren't failures, they were corruptions. Pixel arrays that normally captured crisp images of Earth's surface or deep space returned scrambled data, geometric patterns that looked almost digital, as if the incoming light had been encoded rather than simply recorded. She obtained sample images from contacts at NOAA and the European Space Agency. The corrupted frames showed repeating structures, blocks of pixels that alternated between maximum and minimum values in checkerboard patterns. Image processing software interpreted the corruption as catastrophic sensor failure. But when Vasquez analyzed the raw data, she found something extraordinary. The patterns weren't random noise, they contained periodicity, structures that repeated every 4.7 seconds within each corrupted frame. She ran Fourier analysis on the pixel values, converting spatial patterns into frequency components. A sharp peak appeared at exactly 0.21 Hz, the same frequency that had appeared in magnetic field measurements, solar wind data, and now visual observations of 3I/Atlas. The object was somehow modulating electromagnetic radiation at a specific frequency, and that modulation was corrupting any detector that tried to observe it. Vasquez proposed a mechanism. If 3I/Atlas generated a pulsed magnetic field at 0.21 Hz, and if that field was strong enough, it could interfere with the electronics in camera sensors.
Charged particles in the sensor arrays would experience forces from the oscillating magnetic field, creating false signals that overwrote the actual image data. It was theoretically possible, but would require a magnetic field strength far beyond what any natural object should produce. Dr. Chen tested the hypothesis using data from Parker's solar probe, which had approached within 15 million kilometers of 3I/Atlas during the comet's perihelion passage. Parker's magnetometer had recorded field strengths of 80,000 nanoteslas when the probe briefly passed through the comet's vicinity. For comparison, Earth's magnetic field at the surface is about 50,000 nanoteslas. A comet, essentially a frozen dirt ball, was generating a planetary strength magnetic field, and that field was oscillating at exactly the frequency that corrupted camera sensors and coincided with the comet's visible dimming pulses. The implications were staggering. This wasn't passive light absorption. 3I/Atlas was actively generating electromagnetic interference that prevented clear observation. The object appeared to possess the capability to detect when it was being watched and respond by creating conditions that degraded or prevented imaging. Dr. Takahashi coined a term for it during an online discussion with colleagues: adaptive camouflage. The comet was behaving like certain animals on Earth that change their appearance to match their surroundings, except 3I/Atlas was adapting to match the observational techniques being used against it. On November 12th, a team at MIT's Haystack Observatory attempted a different approach. If optical and infrared observations were being disrupted, perhaps radar would work. Radar doesn't rely on reflected sunlight or thermal emission. It actively transmits a signal toward the target and measures the echo. The Haystack radar, normally used for tracking satellites and space debris, was powerful enough to detect objects at lunar distance. 3I/Atlas was much closer, well within the radar's range. The observation was scheduled for a 4-hour window. Haystack's 37-meter antenna transmitted a continuous wave signal at 10 gigahertz directly toward 3I/Atlas's predicted position. For the first 90 minutes, no echo returned. That wasn't surprising. The comet's nucleus was small, and radar cross-sections of icy, irregular bodies are notoriously difficult to predict. Then, at 21:47 UTC, a signal appeared. Not the broad, diffuse echo expected from a comet nucleus. A sharp, strong return that lasted 23 seconds before cutting off abruptly. The echo was coherent, maintaining a constant frequency and phase that indicated reflection from a smooth, rigid surface, not a tumbling, irregular ice ball. Dr. Stephen Barker, the radar astronomer leading the observation, immediately retransmitted. No echo. He tried again 15 minutes later. Still nothing. Over the remaining 2 hours of the observation, Haystack transmitted continuously toward 3I/Atlas. The single 23-second echo was the only response. Barker analyzed the return signal. The radar cross-section derived from the echo's strength suggested a reflective area of approximately 25,000 square meters. For a spherical object, that would correspond to a diameter of about 90 meters. But previous optical observations had estimated the nucleus at 180 to 200 meters. Either the radar had illuminated only part of the object, or the reflective surface was substantially smaller than the visible coma suggested. More disturbing was the echo's characteristics. Natural surfaces scatter radar in all directions. Some signal returns to the transmitter, but most energy reflects away. The echo from 3I/Atlas showed minimal scattering. Nearly all the transmitted energy that hit the object came straight back to Haystack, as if the surface was specifically designed to return radar signals toward their source. That kind of retroreflection requires either very specific geometry or engineered surfaces. Naturally occurring retroreflectors are extremely rare and certainly don't exist on comets. The scientific community remained divided, but the division was no longer about whether 3I/Atlas was unusual. That was established. The division was about what unusual meant. One camp, led by researchers like Dr. Benjamin Torres at NASA, argued for exotic but natural explanations. Perhaps 3I/Atlas was a fragment of a disrupted planet from another star system, carrying metallic materials that generated strong magnetic fields when heated by the sun. Perhaps its surface was covered with pure carbon or other light-absorbing materials that produce the dimming effects. Rare, yes. Unprecedented, certainly. But ultimately natural. The opposing view, quietly gaining support among researchers who had direct experience with the observation failures, suggested something more radical. Dr. Longbrook published a preprint paper on November 16th titled Adaptive Electromagnetic Camouflage in Interstellar Object 3I/Atlas, Evidence for Non-Natural Origin. The paper compiled the observation failures, the electromagnetic interference, the synchronized dimming events, and the radar retroreflection. Longbrook's conclusion was carefully worded but unmistakable. The probability that all observed phenomena resulted from natural processes was vanishingly small. The evidence pointed toward artificial origin, an object designed with capabilities to avoid detailed observation. The paper was downloaded 50,000 times in the first 48 hours. Academic responses ranged from cautious interest to outright dismissal. But outside academic circles, the implications spread rapidly. If 3I/Atlas was artificial, if it possessed technology to mask itself from observation, then every assumption about its purpose and destination required reevaluation. It wasn't just an interstellar visitor passing through. It was an object with intent, capable of responding to human attempts at observation by actively preventing them, and it was doing this while executing precise trajectory changes that would bring it through Earth's magnetotail in less than 3 weeks. On November 18th, NASA issued its most detailed public statement yet on 3I/Atlas. The statement acknowledged observational challenges and confirmed that multiple attempts at high-resolution imaging had produced inconsistent results. It attributed the difficulties to the object's unique electromagnetic properties and highly variable surface characteristics. The statement made no mention of adaptive camouflage, artificial origin, or the possibility that 3I/Atlas was deliberately avoiding detection. It concluded with assurances that monitoring would continue and that any significant new findings would be communicated promptly. Dr. Simmons, reading the statement in her office at the Space Telescope Study Institute, noted what it didn't say. It didn't deny that something extraordinary was happening. It just declined to speculate about why. And in the careful language of institutional science, that omission spoke louder than any explicit acknowledgement could.